Today's lesson we are going to talk about solving 2 by 2 first-order linear systems of differential equations using the matrix method. We often call this method Euler's method as well. So we heard an introduction. First-order linear systems of differential equations describe the evolution of variables whose rates of change depend linearly on all variables. The system with two unknown functions describes a point that's moving in an xy plane. So the matrix method provides a complex way to solve such kind of systems. So here, let's look at the problem generally. A 2 by 2 first-order linear system can be written as this form, and we know this system is homogeneous system because there are no f function here, or we can write this system in matrix form, which is this one, and where A is vector of constant numbers, x is vector of x and y. Here, a11, a12, and 21, 22 are constant numbers. Here, A determines how each variable influences itself and the other variables. The solutions depends entirely on the eigenvalues and eigenvectors of A. So, according to the Euler's method, which is we call matrix method, we try to get the solution as the form of this. So we substitute this one into this system. So we can get from this one, we can get this equation. And to solve this kind of equation, we have to know the form of the characteristic equation. Non-trivial v exists only if the determinant of a minus lambda I equals 0, where I is unit matrix. For a 2 by 2 system, from this equation, we can get the quadratic equation, this one. So solving this quadratic gives the we can get the eigenvalues lambda 1 and lambda 2. But there are we have 3 cases, which one of them is here lambda 1 and lambda 2 can be different real values, and the second they can be repeated, and the third one they can be complex numbers. So let's look at the first one. We consider here lambda 1 and lambda 2 are distinct real eigenvalues, and they are not equal to each other. So, in this situation, there exist 2 independent eigenvectors, which are v1 and v2, and the solution form can be this. For example, let's look at this system. In the matrix form, we can write A as this form, and if we find the characteristic equation, which is this, we find the solutions of the characteristic equation. Lambda 1 equals 4, lambda 2 equals 2. So we can see here these eigenvalues are not equal to each other and they are real. So in this situation, we the case 1 distinct real eigenvalues. we have the distinct real eigenvalues. And we have to know the eigenvectors to get the fundamental matrix of the system. If lambda 1 equals 4, we can get the V1, eigenvector V1 equals 1, 1. And if lambda 2 equals 2, V2 equals 1 and minus 1. And using them, we can get the solution, which is this form. In the case 2, repeated eigenvalues. Sometimes the eigenvalues can be repeated. So here we answer the question, what we do, we have the repeated eigenvalue when we have the repeated eigenvalues. If the eigenvalues is repeated, which means lambda 1 equals lambda 2 equals lambda. And there is only one eigenvector. We cannot find the second eigenvector here, but we can find using this method, which is a minus lambda e, where ei is unit vector, is multiplied by v2 equals v1. So, and the general solution can be the form of this here. For example, let's look at this systems of differential equations. X prime equals 2x plus y and y prime equals 2y. So in the matrix form, here A equals 2, 1, 0, 2. And here we can get the eigenvalue, which is lambda equals 2. So in this situation, we have only one eigenvalue, but it's repeated twice. So according to this method, we can get the eigenvectors as V1 for the lambda 1 equals 1, 0. Generalized vector V2 can be 0, 1. So using them, we can get the solution, which is the form of this according to this formula. So there is one case left, which is third one, complex eigenvalues. We have one case left, which is the eigenvalues are complex. If the eigenvalues are complex, which means lambda equals alpha plus minus I theta, the system exhibits rotation or oscillations. Eigenvectors are complex and their real solution is obtained by separating real and imaginary part of this this one. So here u of t, real part of this, and w of t is the imaginary part here. For example, let's look at this system in the matrix form. A equals 0 minus 1, 1, and 0. And solving the characteristic equation, we can get lambda equals plus minus 1i. And here, eigenvector is 1 minus I. Real solution of the system, u of t cosine t, sine t, and w of t minus sine t and cosine t. Using them, we can get the solution for that system. When we have the complex eigenvalues. So general solution can be this form. So here is in conclusion, eigenvalues determine growth, decay, or oscillations. Eigenvectors determine directions of motion, and repeated eigenvalues may require generalized eigenvectors. And overall, we have gone through the method, which is called matrix method, in this lesson, and that's the end of the lesson.